Hi everybody, it's Mr. DeCrane, and in this video we're going to be talking about how to graph logarithmic functions. So let's start out with this basic one, y equals log base 2 of x. And you may think to yourself, I don't know how to graph these, how am I supposed to do this problem? Well, think about something you do know how to do. For example, you already know that you can translate y equals log base 2 of x into an exponential equation. We can write that as 2 to the y equals x. And you can actually find ordered pairs for that. Remember, anytime you want to graph something, all you're doing is finding all the ordered pairs that satisfy that particular equation. So if I want to find ordered pairs that satisfy 2 to the y equals x, I need to pick some y values, because once I pick a y, I can calculate x pretty quickly. So let's pick some y values that we know. For example, when y is 1, 2 to the first power is 2, x has got to be 2. When y is 2, 2 squared is 4, so x is 4. When y is 3, 2 to the third power is 8, and when y is 4, 2 to the fourth power gives us 16. And you may be noticing that you're used to writing those 1, 2, 3, 4 numbers in the x column, and these 2, 4, 8, 16 numbers in the y column. But that's because we often do we've been graphing before the inverse function 2 to the x equals y. So this is a little bit different. This is the graph of the inverse of that exponential function. Remember, if we go backwards, if y is 0, then x is going to be 1. If y is negative 1, 2 to the negative 1 is a half. If y is negative 2, 2 to the negative 2 is 1/4. If y is negative 3, 2 to the negative 3 is 1/8. And so now all we do is plot these points. So pause the video for a moment and get out your grid paper and see if you can plot those and make sure you get them all in the right spot. I'll wait for you. Okay, you got the points plotted? Here's the three where x equals 1, 2, 4, and 8. 16 is off the grid, so I didn't plot that one. Be careful how you plot these ones with fractional values of x. If x is 1/2, then y is going to be negative 1. When x is 1/4, so it's getting really close to the y-axis here. Y is negative 2. And when x is 1/8, I don't know that I can even let's see, I'm just going to put it right there, almost on the axis. It's not quite on the axis. And I want you to notice that as I make the y values more negative, in other words, as I travel down the axis here, my x values get smaller and smaller, closer and closer to 0. That means that there's an asymptote here at the line x equals 0, or the y-axis. That's an asymptote. So when I connect these dots up, I'm going to connect them in a nice smooth curve, and over here I'm just going to draw it really close to the axis. Remember, an asymptote is a line that the graph gets really close to but never quite reaches. And so that's the graph of y equals log base 2 of x. Some important features to note. As usual, we should talk about domain and range. Well, the domain here, what values could we pick for x? And you'll notice the graph never ever goes over on this side of the grid. So the domain is x is bigger than 0, and the range is all real numbers, because I can pick anything I want for y to plug in for that exponent. There's an asymptote, as we said, at x equals 0, and we have an x-intercept at 1, 0, there is no y-intercept here. So those are important features that we should keep track of. I'd like you to try one now. So here's one to give a shot. Y equals log of x. And remember, if there's no base written in the logarithm, we understand that it's base 10. So what I'd like you to do is try making a table of values and graphing the ordered pairs for y equals log base 10 of x. Pause the video and do that. I'll wait for you. So here's the table of values, and here's the graph. You notice I can only plot 3 of the points because the other ones get really, really small. In fact, this 1/100th comma negative 2, I've got to get that almost right on the axis. And so when I go to graph this, I've got to make it really flat up here. And you notice it's not going to even get up to this y equals 2 line until x is out at 100. So it grows really slowly, but it does keep growing. Back over here, this is going to get right along the x-axis again. Our asymptote is again x equals 0. Now you may be asking yourself, hey, what's the difference between this log graph and the one we just did, and can I tell how steep it's going to get? That's a really good question. Something to note is that this base actually tells us how quickly the x values grow. You can kind of see here they go up by a factor of 10 every time. on the graph, that means I've got this x-intercept that's 1 unit away from the asymptote, and the next point is way out here 10 units away from the asymptote. If we look back at our log base 2 graph, the x values here are going up by factors of 2. I multiply by 2 every time. So when my x-intercept, oops, that's scratched out. When the x-intercept is 1 unit away from the axis, the next point up is 2 units, and the next point up is 4 units away, and the next point up is 8 units away. So that base 2 tells us about how fast the x values are growing in relationship to the y. Let's try a slightly more complicated one, y equals log base 3 of the quantity x plus 6. Go ahead and give this one a shot. I'll wait for you here. So I didn't really do the whole complete thing, but I want to walk through a couple of steps to see how you're doing with this. Y equals log base 3 of x plus 6 can be translated into the base 3 to the y equals x plus 6. And again, we can pick a value for y to figure out x. So when y is 0, 3 to the 0 is 1. And so I'm thinking here, 1 equals x plus 6. Well, then x has got to be negative 5. When y is 1, 3 to the 1 is 3. So I've got 3 equals x plus 6. So if I subtract 6 from both sides, I get negative 3 for x. When y is 2, 3 squared is 9. So I got 9 equals x plus 6. So x must be 3. When y is 3 rather, 3 cubed is 27 equals x plus 6. X has got to be 21. So those get pretty big. Let's plot those out. So 0, negative 5. 1, 2, 3, 4, 5 is right there. Negative 3, 1 is there. 3, 2 is over here. And 21, 3 is too big to put on the graph, so I'm not going to do that. What if y is negative 1? Remember, 3 to the negative 1 is 1/3 equals x plus 6. So if I subtract 6, 1/3 take away 6 is going to give me negative 5 2/3. So if I'm back here, negative 5 is here. If I go backwards 2/3 more, then I can go down 1 on the y-axis. And let's see, 3 to the negative 2 is 1/9 equals x plus 6. So if I subtract 6, I'm going to get negative 5 8/9. So that's really getting close to negative 6, isn't it? I'm never actually going to get all the way to negative 6. In fact, that asymptote is going to be here at x equals negative 6. And so when I draw the graph, again, I just make that basic log shape. It gets really close to the asymptote here. My domain is x has got to be bigger than negative 6. My range is going to be, actually it's all real numbers, isn't it? Because I can pick any number I want for y in this particular one. And the asymptote is at x equals negative 6. Remember our idea about transforming functions. When you see an x plus 6 in here, this just means shift left 6. And what are we shifting left 6? The parent function is y equals log base 3 of x, which looks just like the other log graphs we've already drawn, and all we're doing is shifting it. Sorry, I'll make that better, easier to read. When we're shifting the basic log graph left 6, so instead of being on the y-axis rather, if that's where my asymptote is for most log graphs, but when I shift left 6, it's over here at x equals negative 6, but the shape is the same. And again, note please that if we look at the asymptote, that x-intercept is 1 off the asymptote, the next point up is 3 off the asymptote because that's a base 3 function. Hopefully this helps you understand how to graph log functions. Enjoy and keep graphing.